A gyroscope is a spinning wheel or disc in which the axis of rotation is free to assume any orientation by itself. When rotating, the orientation of this axis is unaffected by tilting or rotation of the mounting, according to the conservation of angular momentum. Because of this, gyroscopes are useful for measuring or maintaining orientation. Gyroscopes based on other operating principles also exist, such as the electronic, microchip packaged MEMS gyroscopes found in consumer electronics devices, solid-state ring lasers, fiber optic gyroscopes, and the extremely sensitive quantum gyroscope. Applications of gyroscopes include inertial navigation systems where magnetic compasses would not work, as in the Hubble Telescope, or inside the steel hull of a submerged submarine, or would not be precise enough. Due to their precision, gyroscopes are also used in gyrotheodolites to maintain direction in tunnel mining. Gyroscopes can be used to construct gyrocompasses, which complement or replace magnetic compasses in ships, aircraft and spacecraft, vehicles in general, to assist in stability. Hubble Space Telescope, bicycles, motorcycles, and ships, or be used as part of an inertial guidance system. However, it should be mentioned that Dr. Robert E. Klein of the Mechanical Engineering Department, University of Illinois at Urbana-Champaign, showed conclusively, by a sequence of experiments, that gyroscopic action is not needed for the stability of a bicycle. A gyroscope is a wheel mounted in 2 or 3 gimbals, which are pivoted supports that allow the rotation of the wheel about a single axis. A set of 3 gimbals, one mounted on the other with orthogonal pivot axes, may be used to allow a wheel mounted on the innermost gimbal to have an orientation remaining independent of the orientation, in space, of its support. In the case of a gyroscope with 2 gimbals, the outer gimbal, which is the gyroscope frame, is mounted so as to pivot about an axis in its own plane determined by the support. This outer gimbal possesses 1 degree of rotational freedom and its axis possesses none. The inner gimbal is mounted in the gyroscope frame outer gimbal so as to pivot about an axis in its own plane that is always perpendicular to the pivotal axis of the gyroscope frame outer gimbal. This inner gimbal has 2 degrees of rotational freedom. The axle of the spinning wheel defines the spin axis. The rotor is constrained to spin about an axis, which is always perpendicular to the axis of the inner gimbal. So the rotor possesses 3 degrees of rotational freedom and its axis possesses 2. The wheel responds to a force applied to the input axis by a reaction force to the output axis. The behavior of a gyroscope can be most easily appreciated by consideration of the front wheel of a bicycle. If the wheel is leaned away from the vertical so that the top of the wheel moves to the left, the forward rim of the wheel also turns to the left. In other words, rotation on one axis of the turning wheel produces rotation of the third axis. A gyroscope flywheel will roll or resist about the output axis depending upon whether the output gimbals are of a free or fixed configuration. Examples of some free output gimbal devices would be the attitude reference gyroscopes used to sense or measure the pitch, roll and yaw attitude angles in a spacecraft or aircraft. The center of gravity of the rotor can be in a fixed position. The rotor simultaneously spins about one axis and is capable of oscillating about the 2 other axes, and, thus, except for its inherent resistance due to rotor spin, it is free to turn in any direction about the fixed point. Some gyroscopes have mechanical equivalents substituted for one or more of the elements. For example, the spinning rotor may be suspended in a fluid, instead of being pivotally mounted in gimbals. A control moment gyroscope (CMG) is an example of a fixed output gimbal device that is used on spacecraft to hold or maintain a desired attitude angle or pointing direction using the gyroscopic resistance force. In some special cases, the outer gimbal or its equivalent may be omitted so that the rotor has only 2 degrees of freedom. In other cases, the center of gravity of the rotor may be offset from the axis of oscillation, and, thus, the center of gravity of the rotor and the center of suspension of the rotor may not coincide.
We're taking smartphone spaceship technology on a motorcycle platform with the safety of a car. Basically, it's a robot motorcycle. It self-balances and really increases your safety and your range and the excitement of riding a motorcycle. 200 miles per charge. It's a two-wheel drive, wheel hub motored, electric vehicle. Steer it like a car. You sit in it like a car. You have pedals like a car, but the robot side, it takes your steering input and leans you into turns, a lot like a jet fighter. So as you can see, full electronics in here. And this is actually our real gyro right here, if you want to take a look at this. The gyroscopes inside basically output around 1,300 foot-pounds of torque. So you basically need a baby elephant to knock it over. It's a lot like a CMG or a control moment gyro. The International Space Station and most satellites use the same orientation technology. We've just kind of taken that and made it commercially available. There are servos and there are gyro motors, there are traction motors, but sensors like an IMU, IR sensors. There's actually a lot of temperature and heat sensors, a myriad of sensors that actually all feed data, and that has to be processed. And through that process, a command to the gyros to tilt and lean the vehicle to keep it balanced, or either to lean into a turn. All it's very dependently based on our processing system. The prototype that we have now uses two i7s. At our end product, we should be using something that would power a smartphone today. One of the hurdles in our development is having the vehicle actually be more aware of its surroundings. So it's kind of like putting AI, but also having good sensory perception of the road, of any kind of external influences or disturbances, and having that all get computed and processed to allow for stability in all scenarios. On the heads-up display, you can see battery life, range, how much left you have in your procession budget. It's kind of like your artificial horizon. And also, it's basically a rolling smartphone, so all of the information on your smartphone will be on a side panel. Upgrading the hardware, the gyro can be done pretty easily. The gyros actually come, and the battery pack come in its own modular unit. So you can upgrade the gyro output, you can upgrade the battery size, or both. So if you want a faster, more robust, more stabilized, C1, it's pretty easy to upgrade that. The chassis is made out of steel. We could be using some kind of composite body for the interior as well. Parts count, we're 1/10 of a part of a car. Cars typically have around 24,000 parts. If you drive an Audi, it's 40,000. We only have 2,239. So it's pretty easy to manufacture. That's why we can make it affordable. In our audience, urban professionals, tech junkies, they have to have the first thing. They commute, they have a professional life. They still want to have fun, and they want to have the first best thing, but at an affordable price.